Hey everybody, this is Larry. This is the 8th day of the July Leetcode Daily Challenge. Hope you have a good day. Hit the like button, hit the subscribe button, join me on Discord, come hang out and ask questions. Today's problem will be threesome, which is a very early well-known Leetcode problem. So I've solved this in a couple of different ways. So you actually get to, and I actually solved this a week ago on my Twitch stream, which you can also check out the link. As a request to someone. So I actually was trying to solve it a different way today. But I'll go over the two ways that you could solve it, that I did solve it. And you let me know which one you like more. So three sums. So you have an array of nums 3. Actually, I'm going to try to see if I can pull up my solution. Because I have today's solution, but I also want to pull up my solution from last week so I could go over it again. But basically the idea is that given these three numbers A, B, and C, how can you take advantage of, or how can you create structure in a way that you can go through it really quick? And the way that I did it was by, first sorting it. You'll find that sorting it makes a lot of things, gives you a lot of nice structure. But the idea is that, okay, and I actually did the formula wrong if you watch me do the code live, so you have to be careful. I wasted a little bit of time there, but basically you're given a formula A plus B plus C is equal to 0, and the extension from two sum is that, okay, you have A plus B is equal to 0, so then A is, you just have to look for A where or B such that A is negative B, something like that, and then here you have A plus B plus C is 0, 0. So we have to do a similar thing where, let's just say we have a fixed A, right? Then that means that we're trying to get B plus C is equal to negative A. And that's pretty much my strategy for solving this, for this version of my solution, is that, okay, so I'm fixing A, and now I do, so target is A, and then now I go use the two pointers algorithm, because the way it's sorted, you could use the two pointers algorithm because your biggest number have to minus your smallest number to get that the invariant of closest to A, or negative A in this case, and then as you go close, as the number goes closer, they will still ideally remain close to A distance away. So that's kind of the strategy behind the two pointers, and I was kind of rusty on this one, to be honest, so you'll watch me do it live. But basically I have a left pointer and a right pointer, and and every loop I just check, do all three numbers add up to 0? If it is, then we put it into the array list. If it's not, then I just check, does it make sense to go left or the right? And you just do this by having this formula where you check whether, okay, given these three numbers, and you should prove it to yourself a little bit, but for example, let's say you have, and this is just case analysis, so A plus B plus C is equal to 0 is our case. Let's just say, for example, okay, we'll put the A on the other side again, on negative A. And you know that in this case, because of the two pointers algorithm, B can only go up, right? B can only go up, and C can only go down, right? Meaning that B will increase in value, or C will increase in value, right? So that means that if B plus C is less than this target negative A, because only C can go down, then you want to move the C down. In converse or inversely, if B plus C is greater than negative A, then oh wait, I think I mixed that up, sorry. Let me explain that again. So if B plus C is already smaller than negative A, that means we need a bigger B plus C to be negative A, right? And in this case, you move the B up to get the bigger number to see if it fits this time. And conversely, if b plus c is greater than negative a, that means that the number is already too big, so you need the b plus c sum to be smaller. So then you move the c down. And that's kind of what I have for left and right, is that if the negative target is bigger than the sum, then we move the left, we increment the left so that we get a bigger number, and conversely to get a smaller number. Yeah, and the only thing that I do to optimize, which you need to, maybe the Leetcode's a little bit slow this time of the day, because it's a new problem, is that if two adjacent numbers are equal, then we already did the work, right? Meaning that because if this number is next to this number and they're the same, then you literally already did the problem before, because you have the same numbers, except for like now you have one fewer number, but that shouldn't change anything. If anything, that's just fewer numbers, right? So that's kind of the strategy there, and the same reasoning for incrementing left and right while we go through the array. Yeah, so that's solution one. Let me know what you think about this idea, because I was just playing around with it today, and I had some confusions about how to optimize this, but I think this is the best way that I would think about it. And then the second way that I did it was from last week, was also slow, though faster, but I think the server was faster that day. It's by using a hash table. And basically the idea there is that, okay, for every number, we put every number in a counter, right? Okay, let's put this so then we can see. Hope y'all are still having a great day, great month. Keep everything safe and stuff. Stay safe. Okay, but yeah, again, we sort, though I think in this case we actually don't need to anymore. But basically we put everything in a counter, meaning, you know, if there's 2 1s, we put 2 1s in a dictionary with the count of the numbers that we've seen. And then now we know that we brute force I, J, and K, right? So for J and K, we just have to do the thing, and we again skip duplicate numbers because we already solved that problem before. And then now the current sum is equal to, now you have J and K, then this is I, or the negative I to be exact. And then we just see if these 3 numbers are possible. And they're possible if depending on scenarios, but it just counts the numbers of things that are possible, meaning that if A is equal to B and B is equal to C, that means that all 3 numbers are the same, right? And that means that we just want to make sure that we have 3 numbers at the same, that are in the lookup table, right? Because if there are only 2 numbers and you try to use 3, then that's no good. That means we don't have enough of these numbers to use it. And that's the same logic for these 3 other cases, and the last one of, okay, if 2 numbers are the same, then we check for that. Or if they're all unique numbers, then we just check for that. It's a little bit hackier, but I find that it's a little bit more intuition, because there are no fancy algorithms. It's just hash tables and just saying what you mean. The only thing that's a little bit tricky is that you have to put them in a set, and I did that by sorting them and then putting them in a set so that you dedupe much easier that way. So that's all I have for the explanation part. Both algorithms will be O of n square, and this one is O of n space. This one, well, they're both O of n space-ish in that that's the auxiliary space, but it's ultimately going to be dominated by the size of your output in terms of space usage, because it may have a lot of pairs, right? So yeah, that's all I have for this problem. I hope you like one of the 2 ways of solving it. Let me know which way you prefer. Let me know which way you like. Hit the like button, hit the subscribe button. Watch me do live next now. Hey everybody, this is Larry. This is me doing the live July challenge coding portion. Let's get started. Week 3 or week 2, 3 sum. Given an array nums of integers are their elements a, b, and c, nums such that a, b plus c is equal to 0. Find all unique triplets in the array which gives the sum of 0. Okay. Yeah, so let's get, I I actually did this problem on my Twitch stream like last week. So I might post that somewhere as well. But this time I'm going to try to do it. I think I did it last time a little bit funky. So I'm going to try to do a little bit different. I think the first thing I'm going to do is just sorting it, and then yeah, maybe I'll have a set for the results, so then I can return the latest version of this. But okay, so the other thing that I wanted to do this time instead is just using the two fingers algorithm, so that because given if you have two sum, for example, where two numbers sum to 0, well, you could just if the array is sorted, then you just walk until they meet in the middle, because and you have to do some maths to kind of make sure that which one is closer to 0 and so forth, so that that it converges. We'll do the same thing with 3 sum, though. I think right now I have to figure it out exactly how that fits in exactly. But yeah, let's start it. Actually, let's do n is equal to the length of nums. And then now let's just say we have some target is equal to nums of index. That means that we could do it either way, but let's just say that this means that for some other a plus target is equal to b. Okay, so yeah, so that means that a minus b is equal to negative target, and that's pretty much the thing that that's the invariant that we'll try to do. So yeah, let's get started. A is equal to, well, I guess a index or left index. Left is equal to index plus 1. Right is equal to n minus 1. Yeah, so while left is less than, is it to right or oops. Yeah, it should be okay. So now okay, so if nums minus left minus nums minus right, actually the other way around. No, it should be, this should be right, because we want our left to be the small, well, given a, b, and c, I guess it doesn't actually matter. I'm trying to think whether this has to be, because right is the bigger number, but then now we're just checking whether this is equal to negative target. So yeah, then we could put it into the set. Do we put the index? Nope, we put the actual value. Okay, I'm just thinking about whether there'll be duplicates. And since index is smaller than left, which is smaller than right, then there shouldn't be duplicates, or not duplicates, but like, do I have to renormalize it in terms of like, like you don't want to return -101 and then 0 -11. So so yes, actually, and also to write it slightly better. Maybe this should have been a, but in any case, so that's num sub index, num sub left, num sub right. And then which one do we move? Because then now we want to either move left to the right or right to the left. So which one will give us more? So if num sub left plus 1, there may be a lot of edge cases, so I'm trying to think about it. If this minus target is greater than not sure if there's an easier way to, minus 1. I know that is double negative, but I just wanted to make it slightly easier to read in terms of how I, say it out loud. But definitely could, move that otherwise. We want to get to smaller ones. Else left 1. We might also have to make sure that this doesn't go over. That's a lot of. I'm just thinking right now where I can write this easier, but maybe I should just leave it this way a little bit. We are else if same thing that we were doing, pretty much. Yeah, they're not the same. Actually, I guess it doesn't really matter. We can actually just do that and then maybe bring this up. And then let's give it a go. So I feel like, there are a couple of things that we don't take care of. I just want to see if it would at least give us on the right track, which it has not, unfortunately. So right is inclusive. Yeah, okay. Maybe my directions are in the wrong way. Can't imagine. That's a little bit. I thought that it would at least do one more. Huh. Or like give us one answer. Sorry that I got the signs wrong. Target is -4. This is this getting it to? Well, this was at 1. So no, I was moving the wrong side. I guess there was no answer for this one. I guess that's fair. But this should be correct. So maybe my math is wrong. Negative. Why did I write it like this? Okay, let's just write target plus this is equal to this. Still no though, but this should be. Oh. This should clearly be right? Oh wait, that's not right. It should be okay, I just used the wrong formula at all. So this should be this plus b is equal to 0, which means this is negative b, which means this is just really wrong in some way. Okay, Also, that means that's why my formula here, I had to reverse the formula. I just wrote the wrong formula for this one. Silly mistakes. Okay, cool. Yeah. That makes me feel a little bit better, but still not getting the -101. So it's definitely moving the wrong way. Let's see, if this is wrong, then that's okay. -1, -1, 2, and then now this just keeps on increasing the left, which doesn't make sense. That means my formula doesn't really make sense because it was on used to be on the old one. Oops. Well, let's just do which one is smaller by adding all these. So I think this one should be. I had the wrong formula before because I think I was thinking of another problem or something, which happens, I suppose. So in this case, this one is definitely wrong. We want the one that makes it closer to 0. Okay. Yeah, so that now works, but this is probably going to give us an issue at some point in that these might be equal. Maybe that's okay. Because that means that it only happens when left plus 1 is equal to right anyway, so maybe that's okay. All right, let's test a couple of cases. Are there more examples? Nope. I don't know. Let's see. Also, just like empty cases. Cool. It seems like it is much easier to code once you write the right formula. What was I doing? Whoops. Let's see. Oh, wrong answer, huh? Oh, I missed this. Did I not test the 0, case? I thought I tested 0, case. I did, but it misses it here. So it catches all the other case, I want to say. At least for this one. Why does it miss 0? It's probably because how we handle some edge cases. In that I didn't do any. So 001, 9, 10, 11. Oh, 8, it should be 8, 9, 10 at some point. But it keeps on incrementing because they're the same, so we just took. That's interesting. Because we keep on, so the problem was that we keep on incrementing until we keep on incrementing the left until the right goes. I guess on tiebreaker, maybe that's a better way. Okay, but now we're missing another case, so that means that that means that there's an invariant that I wasn't thinking of. Now what case am I missing? Negative? No, that's here. -211. Because now this time it tries to always go down on the right side, so then the middle is not good. Wow. How to handle that? Well, I think what I need to do in this case is that in this case, so this thing only happens when they're both equal to each other, which is really weird. But I guess we have to check for it. And if they're both equal to each other, then what do we do? I want to increment them both at the same time. Would that work? Let's see. What a weird test. I mean, not just weird in how I need to think about it. So what? So in this case, this has to go down. No, sorry. This has to go up. Right? Oh, wait, no. Because this going down doesn't help me anything, right? Then we have to go up. But we were just maxing this thing, so, or minimizing this, so it doesn't really show. So we have to factor in the target. I think that's how we need to do it. Which is that, okay. If target minus no, this should be a plus. No, wait. So basically, let's say these are our current numbers. If this is greater than it, then that means that we need a bigger number, which means that we want left to be +1. Else, right is -1. Maybe that should be good enough. Okay. I just did a lazy thing in analysis in that I just chose the one that gets you closer to 0. But I guess it didn't really work. This one didn't really work either. Are my signs wrong? 5 is smaller than this, so we need a smaller number, which is fine, right? And this should be a answer, right? Is that not an answer? this gives you -1. That means we need a smaller number. So that's why I keep on decreasing. Is my logic wrong? Man, I'm really bad today. Oh no, you want the larger negative number. I think that's where I okay. Because yeah. Okay. That looks way better. Because you want A, B, and C to sum to each other. Okay. Oh no, did I okay, I still have my test cases. Should paste them somewhere though. But okay. Okay, let's give it a go again. Just double checking again, but okay, seems good. Uh-oh. Oh, really? How did that happen? Because there should be n square. Because we always move left and right. So why does this time limit? Okay, so I mean it's a little bit slow for now, but we'll have to do something smarter, I guess. I feel like, well, you can do better than n square, so it's a little bit odd. Guess we have to do a little bit smart about the duping, so that we don't do the same thing twice. But that's such a linear optimization. So here, if if this is equal to index -1, that means that we have already done it. So let's do that. Let's just test it real quick. 1.5 seconds. Let's see what happens for the timing. .8 seconds. Maybe Leetcode service is just running a little slow today, because everyone's submitting. Because that was just slower, right? Yeah, there's a lot of variance. It seems like. I don't know if this helps enough, but how about in this case we also do it here? Is what I was going to say. Nums left is equal to nums of left -1. Yeah, that's the only thing that I was worried about a little bit. Wow. Really? I think, to be honest, it feels like a little bit that it feels a little bit that oh, and in this case, because there's no duplicate, we could make this a list. So I was gonna say, I forgot about that part. I was hoping that was fast enough though, but is the list faster? I don't know. I really think that, well, you can't really do better than n squared, so I don't know how much better you want it to be. I also just think that the Leetcode service is under load right now, so we'll see if it once-ish. Yeah, and that's just like random at this point, right? Like you have to guess micro optimization so that it works. It's not really very helpful for learning. But yeah, I used a lot less memory apparently. Okay, cool. Yeah, that's why for this oh yeah, so the complexity is going to be n squared because we look at, for here, this loop will give you O of n, and here, because you're doing 2 pointers going from left and right, so each index will only get hit once, so that'll be O of n in the inner loop, right? So that's n squared. In terms of space, I guess technically is O of the size of the output, because we don't really use any extra space except for to print out the output, which I guess could be linear. So is that true? Maybe quadratic actually. Maybe not. Should be either linear or quadratic. I have to think about that in a little bit. But yeah, but overall, I don't like that this problem needs you to make a micro optimization. But otherwise, it seems pretty okay, pretty straightforward. I actually usually solve this with a hash table, so that's why today I wanted to push myself to try to solve it another way. I'm actually, since I actually just recorded this video on my Twitch like a week ago, so I'll put it at the end of this video as well, so that you could come and watch how I did it a week ago, which I actually did it a different way. Otherwise, it would just be a waste of your time. It might still be, but yeah. But that's why for today. Hit the like button, hit the subscribe button, and I will see y'all tomorrow. Bye bye. Okay, 15 threesome. Given an array nums of n integers, are there elements a, b, c in num such that a plus b plus c is equal to 0? Find all unique triplets in an array which give us the sum of 0. The solution set must not contain duplicate triplets. Okay. Yeah, I mean, I think that's what I was saying earlier, right? With these problems is that, like, given this, there are really a lot of ways to solve this. And the question is whether, like, what are the constraints for this problem? And, is it, like, what is n, essentially, right? And it's not, and depending on what it is, it could be different answers. So let me just pre-assume that it is not just an n cubed solution or n choose 3 solution if you want to be precise, because then, I don't know, I don't think that would be a medium, because that's just 3 for loops. We could reduce it down to 2 for loops, right? But I don't know if that's fast enough, so let me try that. Because I just actually don't know, because that's the thing, is not knowing whether I need to do better is because I don't know what n is. If n is 1,000,000, then, well, we have to do something better. If because there's also a dynamic programming, kind of, depending on the range of these problems, the range of these numbers. But yeah, again, it's hard to say without knowing what n is and what the numbers are constrained by and stuff like that. So that's why for these problems it's a little bit tricky to get right at the first time. But yeah, so now let's just say for each number, how do we want to do it, right? So basically, the way that I would think about it is that, so we would have, say, 3 numbers. Let's say we have 3 for loops, right? So something like this. Or I guess I use A because that's the vocabulary. And then for B in range, let's just call them IJK. And I know that I'm mixing things up. This is N, and this goes from I plus 1 to N. And this is the naive algorithm. And I'm not intending to submit this, but I'm just kind of using it to showcase my my thought process a little bit. So if this is equal to 0, then you could, I guess this is an answer set. So are we supposed to return an array? Oh yeah, a list of a list. Okay. So then now we can append ijk. Is that the syntax? Yeah, I guess so. And then return answer, right? Okay, let's run this real quick. I know that it's not going to run in time, or I think it's not, because if it is, then it's just a very silly problem. But oh yeah, sorry, this is not. This is if num sub I plus num sub j plus num sub k, the solution must not contain duplicate triplets. That's a so if the same number appears multiple times, does that count? I guess we'll just use a set to sort it out, which is a little bit awkward phrasing, maybe, because even that is not specific enough, right? But let's try the proof first, just to see if it, just to get in a good place. Okay. Okay, so now I guess we have a better understanding of this problem, which is that it's not index dependent in that -1, 0, and 1. So it could be these three, and then it could be 0, 1, and -1, and it's still not good, right? So okay, so now I think we have a better grasp of the problem, and I think that if you're at an interview and you ask a similar problem like this where you're just having confusion, make sure you ask your interviewer and kind of go through, well, like just literally what I said, like, oh, if they're different indexes but they have the same numbers, how do we handle them? Should we handle them? And so forth, right? And here we notice that this is the case. And you can actually, fix that in a different way. But so the first thing I would do to kind of handle that is just do nums, just sort the numbers. And then now we can put this in a set, because now the presumption is that num sub I will be smaller than num sub or equal to num sub j, and that is smaller or equal to num sub k. So that in this case, this will be unique, and a unique triplet. So let's fix that. Is it insert or add? I always forget. And then at the very ends, we could just set it to a list of the set. I think that's okay. I don't know if I need to sort the answer. That's why I'm looking around for it. But okay. Oh, I guess we'll just do it to a tuple, and then we could change it later. Yeah. Okay, so the order doesn't matter in the output. I just want to make sure that that's the case, because we output in a different order and it still seems to be okay. But again, so now we know that this is not going to be good enough for, because it's n choose 3, which is about roughly n cubed over 6 or something like that. You could prove that a little bit, but yeah. So the question is then, how can I reduce this from n cubed to n squared, say? We already know that this is actually n log n, at least the way that we did it. We might not need that later on. But yeah, but now we can kind of notice that for each k, we're just looking for the sum of these two things, right? And seeing whether the sum of these two are in a hash table or something like that. And that's pretty much, or you could do it a couple of ways. Or you could actually do it in a couple of ways, in that you could either put the sum in the hash table, or you could just put this in the hash table, right? But you have to put one side in a hash table so that you could look up all of them. And the thing is that as long as you have this formula, you have this formula of this sum is equal to 0, that means that for now I'm going to put num sub I in the hash table. So let's do that. And the only other tricky thing is that we have to keep track of some other stuff so that we know that we can use duplicates. So now let's put in a hash table real quick. Let me think about how I want to put in a hash table. Yeah, I mean, I think you just have to be careful. I guess that's the answer. But let's just say we have a count table, which is just a hash table, and I'm going to use collections.counter, which is a Python library, but it essentially is a hash table that keeps track. It maps anything to how many counts are there, and then now we do a linear scan for I in range of n. So let's just do count of this, increment by 1. And then now we are able to get rid of this loop in theory, but now we have to be a lot, be careful, I think. So now we go from 0 to n, I from j from I plus 1, and then now we have some number, which is, the current sum, say, is equal to num sub j plus num sub k. And now we know that, so we have this number and we want to find num sub I, right? So how does that matter? So you move the num sub I to the other side. So that means that num sub j plus num sub k is equal to, you move this to the other side, I guess, actually. So num sub I is equal to the negative of this. And that's what you're trying to look for. So yeah. So if current sum or negative version of this is in nums, then we can kind of add it, but not quite. It's not quite right, but in theory, right? Which is num sub. I guess we have to sort it actually first, but this is a very Pythonic thing, or a thing that you do in Python. I don't know if it's Pythonic because it's not great, but something like that. And this should be wrong actually. I think, maybe. Well, okay. I didn't think it'd be that long, though. That's a little bit unfortunate. Oh, no. Sorry, I did nums, but I mean the set, or the count. Sorry. Oops. This should still be wrong for a reason that I'll point out. Okay, well, I also didn't think it'd be that long. Come on. Oh, I didn't update this. Okay. Okay, so that's good. But I mean, I knew that was going to be wrong. but okay, now it is wrong in the way that I expected to be wrong, versus that before it was not. But now we have so now we have three numbers, right? We have current sum, so we can actually just let's step back a second and let's just create another variable, which is I just call it nums I. It's not a real array, but so it's your current sum, right? So now we can do if just real quick. But the reason why this is wrong is because it doesn't keep track of counts. Even though you have a hash table with the count, in this case this is wrong because you only have 1, 2. But so 2 plus 2 plus negative 4 is equal to 0. But you only have 1, 2 in this element, right? So how do you handle this? Well, you just have to keep track of, this is a lot of keeping track, but you just have to take a look at count and then see whether for every number it's smaller than that. So how do I want to so now I'm just thinking a little bit how do I want to handle this in implementation in a way that isn't too yucky. Okay, so I guess we could just I don't want, so there are ways to do it with collections dot counter, but I don't want to do it that way because it's too Pythonic-y, even for me. Okay, so let's just get this sorted list then of these three numbers. So now let's just say this is the answer candidate. Is you go to the sorted, basically you have these three numbers and you sort them so that you could generate a unique triplet, right? And then get rid of this for a second. And then if, and the and then there are only a couple of cases. Does it make sense to enumerate them? No, because then it actually could be, let's see, 1, 2, 3, 4 cases. Is that reasonable? Okay, so there are actually only like 4 or 5 cases, so I'm going to enumerate them, but know that programmatically there are easier ways to do this, and maybe I'll brush up on try to figure out how to do this in a clean way. I actually know how to do it using Pythonic counters and then collections.counter in Python, and then doing a counter difference based on that, and then you could do math on that, but it requires too much explanation. So I'm just going to enumerate this a little bit, which is let's just say that they're all equal. Then we just have to check that in this case, because here we already know that they all sum to 0 if they exist. Oh, I guess I didn't check that part actually. I might have erased it by accident. But if num sub I is in count, then continue, or not in count, whoops. And then let's say we already have the numbers, then okay, now that this this thing is true, then if count of num sub I is greater than 3, or actually just exactly, oh no, it could be a 3, sorry. So let's just start with, this is a little bit messy. Maybe we should use a helper function on this. Yeah, let's actually use a helper function on this. Let's just say, is possible. So let's just say we have A, B, and C. So then now we can do if except in I in count, n is possible with these numbers. How did my indentation get so far? A lot of spaces. Then we have this answer candidate, and then we add it to the set, right? Let's just return true for a second so that we could make sure that this still works, because we made a lot of changes. So yeah, and this works in the sense that it is wrong in the way that we expected, but yeah, it's possible. And this also takes into the counter into effect, which is a little bit abuse of a global or non-local thing, but yeah. So now we can do if A is equal to B and B is equal to C, then we have to check if count of A is greater than or equal to 3, we return true. Right. Else I guess we just return this. And then if what was I gonna say? If A is equal to B otherwise, then that means we return count of A is greater than 2, and that should be good enough. You may ask, we should also check count of C, but that is a presumption. Maybe okay, fine. Actually, we should write it out, fine. But you could actually prove that that's always going to be the case, except for that I think in terms of abstraction and writing modular code, you can't expect the input to be as, like you should write it so that the that assumption is not always necessarily true. But yeah. So this is just the 3 cases where 2 numbers equal each other. Oops. So this is way error prone, which is why I kind of thought of, not a fan of, but, and then now they're all unique, right? So we just have to return count of A. And that's pretty much all I have to do. I think to be more consistent, I do something like this. It's greater than 0. Yeah, so that's okay. Now let's give it some give it a lot more test cases. Maybe a few more anyway, because why not? Okay. Yeah, it looks okay. Let's try the empty case and actually this is the only case where this is only possible if they're all zeros, by the way, but but just to keep it generic. Okay, cool. So let's submit it. It feels okay. Uh-oh. Is it too slow? Oh, no, it's too slow. But that's the thing, right, is that they don't tell you what n is. So then now we have to maybe do a little bit more optimization. And it's just all zeros. Okay. That's a... okay. Okay. I mean, that's one of those things where, like, you see it and you're like, okay, I guess we should have optimized for it, but it's also like, it's a little bit weird, maybe. I don't know. Because now we're talking about optimizations that makes things faster, but not in a, like, the optimizations that I'm going to make, will, like, have the same big O of n, but it's just a little bit awkward. So that's kind of why. So n is 3000 in this case. Because the thing is, right, if n is 3000, in the general case, it will be too slow anyway. It's just that, now we're optimizing for a case where they're not unique, and thus, it does some stuff. So maybe some, I don't know. It's really weird, but yeah, and the way to solve this part is just checking that basically if the number is equal to the previous number, you don't have to do the work again because we already done it because of the unique element, right? Because by definition, then it would not be unique because we're literally testing the same number. So we just have to do something like this, where if num sub j is equal to num sub j minus 1, we continue, and of course we have to check the 0 case. So j is greater than 0, and we can also do the same with k, just for prosperity. Oh, gives me the wrong answer. Oh, because no, well, I printed, but it's okay. Did I return the right answer, or did I return stuff? Huh, it gives me the wrong answer. Okay, but that's still a good practice, because I think we might have oh, sorry, this part is wrong. I just have a lazy, didn't think about it because it's copy and way, but you have to do at least the first element, because so it doesn't have to, it's greater than just k is greater than 0. It's actually greater than j, because it then j or j plus 1? That's what I'm thinking about for a second. Because if it's greater than j, then you'll be comparing it with j. So it has to be greater than j plus 1. Okay. Okay. See, much faster on this silliness. But it still has the big same O of n. It's just depending on how you assume it, I think. My code apparently is really slow, so maybe it's just characteristics of my code. I mean, some of that I've written it in a little bit suboptimal way, but I think it's clearer to understand and read. But yeah, so what is the complexity of this problem? Well, the complexity is that we have O of n squared loop. So it's an and each of them does O of 1 hash table lookups and something like that. So this is O of n squared. For space complexity is O of n, because we only hash the we only hash O of n. So yeah, because we only hash the list once for the if statement, if you will. But in terms of, let's see, let me think about an interview or like this is worth as a value of an interview question. I don't know how I feel about this. It feels okay, but I mean, no, I think it's good. I think it's a good problem. I think it's good enough for an interview. I think I dig it a little bit. I think the only thing is that there are, I think, stepping back and thinking about this as a problem, the things that I'm annoyed by are that like it doesn't give you n, and stuff like that, like different things where it just didn't tell you anything. But I think in general this is a reasonable problem. It's one of those problems that asks you about something naive. It's something naive, and then you could make it less naive by making a couple of optimizations, but the big one being using a hash table to make it go from n cubed to n squared. I think that's the big one for this problem, which is a paradigm that comes up all the time. So if you ever feel like you're missing by an O of n factor, then maybe that's the first thing I would do. For competitive programming, lookup tables and hash tables and stuff like that comes up all the time. Definitely very important, and stuff that you just kind of just gotta do it, gotta learn it. Yeah, that's all I have for problem. Yeah, let me know what you